Good morning, everyone. I am Dipanji from BSc Chemistry Honor second year. Today, I am here to represent chemistry of elements of second and third transition series. In previous chapter, we have discussed the position of transition elements in the periodic elements belong to D block of the periodic table and are located in between S block and P block elements in the periodic table as shown below. The D block elements involve primarily the filling of subshell. The penultimate shell in these elements is being expanded from 8 to 18 electrons by adding 10 electrons. We also attempted to define the transition elements as elements which have partly filled shells either in the elementary form or in their commonly occurring oxidation state. Strictly speaking, this definition excludes zinc, cadmium, and mercury from the D block elements. This is because elements do not have partly filled D shell either in elemental form or in their common oxidation state. The elements of group 12 do not distinctly show the properties of transition except to form the ability coordination complexes with ligands. However, for the sake of continuity and rational classification, the elements of group 12 are included in the D block elements. In this chapter, we intend to explore the chemistry of heavier metals of D block second and third transition series. The heavier metals of D block are highlighted. It is interesting to note that the 3D transition series, the atomic number of elements of the second transition series are filled sequentially from 39 to 48. However, there is discontinuity in the atomic numbers between lanthanum, hafnium and their transition series. In brief, second and third series that involve the filling of 4d and 5d orbitals respectively include the elements with atomic number second transition series deuterium to cadmium. 4d orbitals are gradually filled. Third transition series lanthanum, hafnium to mercury. Electronic configuration of second and third transition series. The general electronic configuration of elements of the second and third transition series can be written n-1 d1 to 10 ns1 to 2, where n-1 stands for penultimate shell, which occupies 1 to 10 electrons in their d subshell, while n stands for the outermost shells that occupies 1 to 2 electrons in the s orbital. Table lists the ground state electronic configuration of the elements of second and third transition series. Deuterium atomic number 39, symbol Y, krypton 5s2 4d1, zirconium 40, zirconium Kr36 5s2 4d2, niobium 41 Nb Kr36 fs1 4d4, molybdenum 42 Mo Kr36 5s1 4d5, technetium 43 technetium Kr36 5s1 4d7, ruthenium 44 Ru Kr36 5s1 4d7, rhodium 45 Rh Kr36 5s1 4d8, palladium 46 Pd Kr36 fs0 4d10, silver 47 Ag Kr36 fs1 4d10, cadmium 48 Kd krypton 36 5s2 4d10, lanthanum 57 La, xenon 54 6s2 5d1, hafnium 72 Hf, xenon 54 4f14 6s2 5d2, tantalum 73 Ta, Xe54 4f14 6s2 5d3, tungsten W, Xe54 4f14 6s2 5d4, rhenium Re, xenon 54 4f14 6s2 5d5, osmium OS Xe54 4f14 6s2 5d6, indium 77 Xe54 4f14 6s2 5d7, platinum PT Xe54 4f14 6s1 5d9, gold 4f14 6s1 5d10, Hg Xe54 4f14 6s2 FD10. General characteristics of second and third transition series. We have noticed clear periodic trends down each group in the chemistry of S and P block elements. However, transition elements of second and third transition series, the elements of 5 and 6 show very strong similarities in their chemistry within a group but show large differences from the elements of the first transition series. This similarity is due to the filling of 4f orbitals in the elements that lie between two rows of elements Electrons in these orbitals are very poorly. The electrons in the outer 6s and 5d orbitals as a poor shielding. The effective nuclear charge increase with the result in atomic covalent and ionic radii of the periodic cis transition elements are reduced to almost same as those in the period irregular or anomalous electronic configuration. In the first transition series, the 4s electrons are filled before the 3d electron in the neutral gaseous atoms. From scandium onward, the 3d level continues to fill regularly with increasing Z, but at the chromium, they appears normally. In case of chromium, electrons are so filled so that the 4s and 3d orbitals are each half filled. This is due to the extra stability associated with half filled orbitals. Similarly, at the copper, the electronic configuration is anomalous because of extra stability associated with completely filled d orbitals. However, the elements of second and third transition series display much more electronic configuration in addition to half or completely filled d orbitals. These are shown in the bold letters: scandium 4s2 3d1, titanium 4s2 3d2, vanadium 4s2 3d3, chromium 4s1 3d5, manganese 4s2 3d6, iron 4s2 3d6, cobalt 4s2 3d7, nickel 4s2 3d8, copper 4s1 3d10, zinc 4s2 3d10, by 5s2 4d1, zr fs2 4d2, nbfs1 4d4, mofs1 4d5, tc 5s2 4d5, ru 5s1 4d7, rh 5s1 4d8, pd 5s0 4d10, ag 5s1 4d10, cadmium fs2 4d10, Lu 6s2 5d1, Hf 6s2 5d2, Ta 6s2 4d3, W 6s2 5d4, Ra 6s2 4d5, osmium 6s2 5d6, Ir 6s2 5d7, platinum 6s1 5d9, Au 6s1 5d10, Hg 6s2 5d10. The anomalous configuration of the elements are attributed in the several electronic repulsion. Atomic and ionic radii of elements of first transition series are well known. However, the atomic and ionic radii of second and third transition series elements are not known with certainty with the exception of few elements. As we move down a particular family, the transition metals in the periodic group, there is an increase in size from first to second transition series, but the size increases from the second to the third transition series is negligible as shown in given below. First Ti 1.32, ionic radii 0.68, element V atomic radius 1.22, ionic radius 0.78. Second zirconium 1.45 0.80, niobium 1.35 0.86. Third hafnium 1.44 0.81, Ta atomic radius 1.34 0.86. Oxidation state. The oxidation number of the transition metals are higher for the first of each row than for the later members. Lower oxidation states are found to be more stable in case of first transition series compared to the element of second and third transition series. The element of second and third transition series have common oxidation numbers than the first transition series. For example, molybdenum and tungsten have +6 and +6 oxidation state. Like many main groups, the highest oxidation number of transition metals is found in the case of oxide. Thus, the highest oxidation state +8 occurs in osmium OS4. The other compounds that exist in high oxidation state, which have not counterparts in the first row, are WCl6, ReF7, and PtF6. It is also interesting to know that superficial similarities in the chemistry of second and third transition series element exist compared with elements of first transition series. The other compound that exists in high oxidation state which have no compartments in the first row are WCl6, ReF7, and PtF6. It is also interesting to know that superficial similarities in the chemistry of second and third transition series elements exist compared with the elements of first transition series. For example, chromium MO and W all forms oxide of oxidation number 6. However, chromium oxide CrO3 is highly oxidizing, whereas MoO3 and WO3 are normal oxides of these metals. Reactivity. The elements of the first transition series are more reactive than the corresponding elements of second and third. The lengthening contraction is majorly responsible for the low reactivity of second and third transition series. As an example, gold and platinum are least reactive. The low reactivity is due to the closeness of valence electron to the nucleus because of your poor screening of 4f electrons. Because of poor screening of 4f electrons, the valence electrons are high, tightly bound to the nucleus and are not readily available for chemical reaction. Stability of complex. Transition metals have the ability to form complex in contrast to s and p block elements. This is due to the small size, highly charged ion availability of vacant d orbital, lower energy in the case of transition metals. The elements of first transition series form the complex with hard donors NO and F, whereas the element of second and third transition series form complete with complex with P, S and heavier chalcogen donors. The coordination number 6 is commonly found in the transition element giving octahedral structure. The coordination number 4 is less common and gives either square planar or tetrahedral structure. Complexes with coordination number higher than 6 are less common for the first transition series. Both are common among early members of second and third transition series. Ligand repulsive interaction became more important with higher coordination number, and thus it is the smaller ligands which allows highest coordination number. There are only few compounds in which the coordination number is 7. There are three geometrical forms known in this case and are shown as monocapped octahedron, pentagonal pyramidal, and tetragonally capped trigonal prism. The capped octahedron is shown by tungsten complex WBr3CO4 negative or by NBOF63 negative. Capped octahedron is formed as the addition of seventh atom at the center of any phase. The pentagonal bipyramidal is adopted by anion species that are F7 3 negative, UF7 3 negative, UO2F3 3 negative. Tetragonal capped trigonal prism is adopted by F7 2 negative, where M is equal to NBOT. This arrangement, by putting a seventh atom above the center of one of the rectangular faces or triangular prism, coordination number greater than 7 are also among the third and second row elements. Coordination number 8 is found in the square antiprism, and as in Na3MoCN6, and dodecahedron as in B and 4 and 3 MoCN8 as shown in the figure. It is important to note that the structure is some line influenced by the counter ions in case of Na3MoCN8 and Ba4N3Mo. Coordination 9 is limit for the covalently bound d block metal complexes because represent the full use of 9 valence orbitals 1s, 3p and 5. The anion ReH and I2 negative has the trigonal prismatic structure with coordination number 9 as shown. Aqueous chemistry. Elements of first transition series have a very rich aqueous chemistry. As a result, it forms a variety of tetrahedral and octahedral complexes and display interesting aqueous chemistry. On the other hand, the corresponding members of the second and third transition series, rhodium and zirconium, do not form such complexes and consequently do not have aqueous chemistry. However, most of the heavier metals, instead of forming simple Catholic complex, prefer to form ionic complexes. In the halo, the ionic complexes of heavier transition elements have very rich aqueous chemistry. Magnetic properties. Compounds with no unpaired electrons are diamagnetic, while those with one or more unpaired are paramagnetic. Most of the transition series compounds are paramagnetic. The diamagnetic arises from the circulation of the electron pair induced by the presence of the applied magnetic field. This circulation produces an induced magnetic moment which opposes the applied field and leads to the molecule being repelled by it. On the other hand, unpaired electrons are represented by applied field introduces a magnetic moment which is aligned with diamagnetic. This effect causes ample to attract the magnetic field. Paramagnetic result from the attraction of spin and orbital angular momentum of the electron with the applied magnetic field. If there is no interaction coupling between the spin and orbital angular momentum, the magnetic moment mu s plus L of one atom or ion is related to the total spin of quantum number and the total angular momentum. Mu s plus L is equal to square SS plus 1 plus LL plus 1. The magnetic behavior of the element of second and third transition metal ions is more complicated and explained as one take into consideration both the spin orbit coupling and the effect of covalent character in metal ligand, where G represents gyromagnetic ratio for a free electron and the value is 2.00023 practically 2. Therefore, the above equation reduces to mu s plus L is equal to 4s s plus 1 plus L plus 1. The units of magnetic moment are per magnetron. Under root 4s s plus 1. This is the fact the spin value of magnetic moment. This provides a good approximation of observed magnetic moment for the first transition metal complexes. It is generally found mu is greater than mu s plus L as shown in table 2.5. In case of high speed d ions such as Mn2 positive and Fe3 positive, L is equal to 0. In this case, mu is equal to mu as this form a knowledge of whether the complex is high or low spin. The number of unpaired electrons in the complex can be easily calculated and its magnetic moment evaluated. Metal-metal bonding. Metal-metal bonding is very rare and very transition series except in metal carbonyls. Mn2 CO10, Fe2 CO9, Fe3 CO12, CO4 CO12 in carboxylate complexes such as chromium acetate, Cr2 CH3 COO4 H2O22 and in solid nickel dimethyl dilixone di DMG2. On the other hand, metal-metal bonding is very common against the heavier transition element of second and third transition series. They form carbonyl with M bond similar to those of first transition series Ru3CO12, OS3CO12, RH4CO12, IR4CO12. In addition, it forms RH6CO16. The heavier metals such as molybdenum, Ru, and RH form binuclear carboxylate complex such as MO2CH3CO4, H2O2. The halide ions of the type Ra2Cl8 2 negative and MO2Cl9 3 negative possess M bond. A unique feature of a set of free 5 elements of the second and third transition series is that these form cluster in which there is extensive metal-metal bonding. The complex cation Nb6 C12 2 positive Ta6 Cl12 2 positive have unusual structure. Both the cationic species 6 metal ions arranged in the cluster at the corner of octahedron with 12 bridging halogen atoms across the corner. In these clusters, there is an extensive metal-metal bonding. Unlike the lower halides of 3D series, the lower halides of MO and W exist as hexamers MO6Cl12 and W6Cl12. These present interesting structure M6X84 positive, where M is equal to MO and W, X is equal to Cl. 6 metal atoms are arranged in a cluster at the corners of an octahedron with 8 halogen atoms located above each of the 8 faces of the octahedron and bonding to 3 metal atoms as shown. Chemistry of ReCl3 is interesting as it is a trimer Fe. The heavier metals such as molybdenum, Ru, and RH form binuclear carboxylate complexes such as MO2, CH3COO4, and H2O2. The halide ions of the type Re2Cl8 2 negative and MO2Cl9 3 negative possess MM bond. Unique feature of a set of 5 elements of the second and third transition series is that these form cluster in which there is extensive metal-metal bonding. Set of 5 element NBMOTAWRC. The complex cation Nb6Cl12 2 positive, Ta6Cl12 2 positive have unusual structure. Both the cationic and ionic species contain 6 metal atoms arranged in a cluster of corners of an octahedron with 12 bridging halogen atoms across the corner. In these clusters, there is an extensive metal-metal bonding. Unlike the lower halide of 3D series, the lower halide of MO and W exist as hexamers. These present interesting structures as Me6X84 positive, where M is equal to MO, W, X is equal to Cl. 6 metal atoms are arranged in a cluster at the corner of the octahedron with 8 halogen atoms located above each of the 8 faces of the octahedron and bonded to 3 metal atoms as shown. Chemistry of ReCl3 is interesting as it exists in trimer Fe3Cl and it consists of a triangle with 3 Re atoms with 3 bridging halogen atoms across the 3 corners and 6 halogen atoms. The bridge to the other Re3Cl9 abundance. All the 10 row transition elements are widely distributed throughout the crust and the oceans. Iron is the fourth after oxygen, silicon, and aluminium. Titanium is the ninth, while manganese is the 12th most abundant element by weight in the Earth's crust. The remaining transition element of second and third transition series are very scarce and taken together. These 20 transition elements constitute 0.025% element among the second and third transition series that plays an important role in the human body. Technetium Tc does not occur in nature. Ionization energy. First ionization energy of an atom is minimum energy required to convert 1 mole of gaseous atom into 1 mole of gaseous unpositive ion. M is equal to M positive plus electron. The amount of energy required in process indicates how strongly the most loosely bound electron is attached by the nuclear charge. It has been observed that the case with which an electron can be removed from transition element metal atom is intermediate between those of S and P block element. The first transition energy and the second and third transition energy of the transition elements are plotted in figure. An inspection of figure 2.7 carefully reveals that into third ionization energy ascends more rapidly than the first and second ionization energy. As a result, these transition metals are better indicated by their third ionization energy. The variations of third ionization energies of these transition elements from scandium to zinc Y to Cd and La to Hg shows that there is a general increase in the ionization energy with a discontinuity after group 7. The discontinuity in the values correspond to the ionization energy from a doubly d orbital. F is equal to Z is equal to 26 3d 4s2 36 4s2. The third ionization for the atom of group 8 to 12 are formed doubly occupied d orbitals, consequently lower because of the increasing repulsion between the paired electrons in the same orbitals in the subsequent elements. This is the discontinuity between the manganese and iron in the first transition series and between ruthenium in the second transition series reflect additional energy required to break into half-filled subshells of Mn2 positive and Tb2, which involves the maximum loss of exchange energy. Similarly, in case of europium, the third transition ionization potential does increase into the third transition series where the F4F configuration is reached. Therefore, it falls back and then increases again and approaching configuration of YB2 positive. In brief, ionization energy increase that regularly across the transition series is for regular in third transition series. Y is ZrCl for the most stable chloride of zirconium when for palladium. An inspection of third and higher ionization energy of D block elements agrees with increase in dropping number due to large effective nuclear charge. This constitutes the third and higher IP of palladium very high, which makes it energetically unfavorable. In addition, towards the end of the transition series, and d orbitals become more core-like. As a result, they are less effective in stabilizing higher oxidation state through covalent contribution bonding. Taking together these factors with higher oxidation state accessible to the right of d block. In addition, there is great loss of exchange of every creating PD4, PD2 plus ZR4, ZR2 plus comparative study of element of second and third transition series. We have already discussed the general characteristic of element of second and third transition series with special reference to the elements of first series in predicting section. In this section, we will like to highlight the chemistry of different elements of second and third transition series, zirconium and hafnium. Group 4 consists of elements titanium, zirconium, and hafnium. Some of the unique properties of these elements are we have already marked that the atomic and ionic rate of transition elements in a particular series decrease with the increase in atomic number. However, compared to S and P block element, the decrease in the radii along a particular series is not regular and uniform. In case of group 4, both zirconium and hafnium have larger atomic and ionic radii than titanium. However, an inspection of the table reveals that both the atomic and ionic radii of zirconium and hafnium are identical. As a result, these elements have similar chemistry. This is primarily attributed to the effect known as lanthanide contraction. All elements possess the outside noble gas code D2S2. The significant difference of zirconium and hafnium and from titanium is that unlike titanium, zirconium and hafnium only forms a few compounds in oxidation state below. For below, most of the stable compounds are in oxidation state. For both zirconium and hafnium, for binary tetrahalide, the tetrahalide can be prepared by standard method. MO2 plus C plus Cl2, MCl4 plus Ca2, HXMX4 gives M plus X2. all tetrahalides in the gaseous state are monomeric and tetrahedral, but in the solid state, these are octahedral coordination through halogen bridging. The tetrahedral halides are readily hydrolyzed. The extent of hydrolysis, however, decreases from Ti2. The TiX4 compounds are hydrolyzed to TiO2, whereas zirconium X4 and HFX4 are hydrolyzed to give ZrOx2 and HFOx2. ZrCl4 is hydrolyzed vigorously by water at room temperature to give oxychloride and is stable to further hydrolyze. ZrCl4 plus 9H2, ZrOCl2 plus 8H2 plus 2HCl. The complex which crystallizes from dilute HCl has been shown by X-ray to contain the ion. Each zirconium atom is surrounded by 8 oxygen atoms, 4 oxygen from 4 coordinated to and 4 oxygen from bridging OH. The coordination number of each zirconium atom is complex is either like titanium chloride and HFCl4 are known to act as good Lewis acids. Therefore, these reactions naturally begin to form stable adducts of the comparison MX412, where L is equal to triphenylene phosphine. Zirconium and hafnium have higher charge in plus 4 oxidation state. There is no partly filled d orbital shell that might have stereochemical preferences and have relatively large sizes. Result the tendency to assume higher coordination number increase with zirconium and hafnium. The example where the coordination number reaches 7 or 8 are known with oxygen fluorine. For example, the structure of an ion ZrF73 negative and ZrF at 4 negative are shown below. The species ZrF73 negative is basically a trigonal prism with an extra ligand attached on the face. There are a variety of 8 coordinate complexes in case of zirconium. These 8 coordinated complexes in the following carbohydrates ZrO2CrO4, ZrACAC4, oxalate ZNA4, ZR oxalate 4, nitrate ZrNO3 4. Oxidation state 3. The reduction of the tetrahalides by the respective metal at high temperature and pressure yields the trihalides, which are colored compounds. 3mx4 plus m mx3 200 to 600 5 से 15 atom. The well known in 3 oxidation state are ZrCl3, ZrP3, ZrI3, HFCl3, HFBr3. Niobium and tantalum. Group 5 consists of the elements vanadium, niobium, and tantalum. Some of the unique properties of elements are summarized below. Niobium and tantalum occur generally together, separated from fractional distillation over M2O5, KHF2HF, K2TAF7, electrolysis TA, K2NBO5, more soluble AlNB. Atomic and ionic radii of niobium and tantalum are almost similar but greater than that of 3D vanadium. Among both niobium and tantalum are metallic. Their chemistry of V in their oxidation state are more similar to those typical non-metal. As a result, they do not form cationic complexes characteristic of a metal. Instead, these form a variety of anionic complexes. The coordination number of niobium and tantalum is in these anionic complexes are generally 7 and 8. The stable binary oxide of niobium and tantalum are the pentoxide M2O5NB or Ta, which are dense white powder. These are obtained by the ignition on their niobium and tantalum compounds in area. These are very stable oxide and extremely difficult to reduce. Halides and oxohalides. Niobium and tantalum form whole halides in their higher oxidation state. The pentafluorides are obtained by the reaction M2O5 CCl4 300 degrees Celsius gives M2Cl10 HFMF5 for a unique feature of niobium, that is it forms the stable pentiodide 5Nb plus 5I2 300 से 400 degree 2NbI5. The pentafluoride are volatile white solids melting below 100 degrees Celsius and boiling near 230 degrees Celsius. They have a tetrameric structure that is characteristic for other pentafluorides with MF6 units and one bridging fluoride between each pair of metal atoms. The pentachloride are yellow crystalline solid and are obtained by direct reaction with metal with chlorine. X-ray reveals that NbCl5 is a dimer in solid state with two bridging chloride giving an octahedral configuration. The halides readily hydrolyze to give oxyhalide of the formula MOX3. Metal is equal to NbF at tantalum. The oxohalides are covalent but less volatile than the corresponding pentalide. The structure of NbOCl3 is polymeric and shown Oxychloride contains planar trinuclear groups which are linked into log chains by oxygen bridges between the niobium. Cl2 NbCl NbCl2Cl. Niobium pentachloride Nb2Cl10 is reduced by pyridine to give niobium for complexes NbCl for Py2. The pentafluoride are strong Lewis acid and give like the natural donors to form the complex and with halide ends. For example, both the pentafluoride and form fluorocomplexes. Lower halides. The lower halides of niobium and tantalum deserve special mention. These lower halides are prepared with the reduction of pentahalide either by heating with metal itself or aluminum. Earlier, it was considered that the lower halide of NP and Te were non-stoichiometric. However, it has been shown that most of the lower halide are in fact cluster compounds with containing with basic unit Ma6X12 positive. The octahedral addition of the halogen bringing along the 12 edges of the electron octahedron and interesting complex example of the lower halide of niobium is Nb6Cl14. It is made by reducing niobium pentachloride with cadmium metal in the red solution. The cadmium is precipitated as cadmium sulfide. Nb6Cl14 consists of discrete ion Nb6Cl12 positive. Molybdenum and tungsten. Group 6 consists of element chromium, molybdenum and tungsten. Some of the salient features. Molybdenum and tungsten are the atomic and ionic radii nearly similar but possess greater values for corresponding of first element Cr in groups on account of similar radii values. Molybdenum and W possess nearly similar chemical properties. Group 6 elements display valencies ranging from group valencies +6 down to 0. The +6 valence is highest. For all the elements, molybdenum and tungsten in the +6 are the most stable and the most common. It is important to note in case of chromium, +3 is the most stable and common. It follows that higher valent chromium, especially in +6, will be the strong oxidant. In fact, chromium +6 is the strong oxidizing agent. On the other hand, MO3 and W3 are strongly reducing. The trioxide MO and W are obtained by heating the metal or other compound in air. MOO3 is a white, whereas WO3 is yellow solid. Unlike CrO3, the trioxide of the MO and W are insoluble in water. MO and WO3 are not attacked by acid other than HF. In alkaline medium, these dissolve to form molybdate MOO42 negative and tungsten WO42 negative that are tetrahedral in shape. Condensation of oxoanions give polyoxoanions and polyoxometallate in the presence of acid. Some of the well-characterized molybdate tungstate ions are MOO42 negative, MO7O246 negative, MO8O264 negative. The structure of polymetate and polytungstate are based on MOO6WO6 anions such containing one kind of metal atoms are called isopolyanions, whereas anions containing more than one metal atom are called heteropolyanions. An interesting element is found during molybdate test for the when yellow precipitate are formed NH42HPO4MOO312. Thus the heteropolyanion is PMO12O43 negative.